Hello, my name is Victor Zberstis, and I'm on the team working behind the scenes on worldcommunitygrid.org, which has been using spare processing time from computers around the world since 2004, putting that computer power to good use instead of consuming electrical power just waiting for that next keystroke or mouse movement. In support of Earth Day, we are launching our newest research project on World Community Grid, the Computing for Sustainable Water project from the University of Virginia in Charlottesville, Virginia, USA. They will be studying how human activity patterns affect the Chesapeake Bay watershed's health, with the goal of finding better policies and applying their research techniques to help other watersheds around the world. Please let me introduce Dr. Gerard Learmonth, who will tell you more about the Computing for Sustainable Water project, now starting to run on worldcommunitygrid.org.
Thank you, Victors. In this webcast, I'm going to describe the Computing for Sustainable Water project developed at the University of Virginia and now running on the World Community Grid. The Computing for Sustainable Water project is focused on the Chesapeake Bay and its watershed in the eastern United States. The Chesapeake Bay is the largest estuary in the continental United States and connects directly with the Atlantic Ocean. As the image to the right of this slide indicates, the watershed drains fresh water into the bay from parts of 6 states and the District of Columbia, our nation's capital. In all, the Chesapeake Bay watershed covers approximately 64,000 square miles, or more than 166,000 square kilometers of land area. The bay itself contains over 50 cubic kilometers of water. Most importantly, the Chesapeake Bay watershed is the home to nearly 17 million persons who depend on the watershed. The Chesapeake Bay watershed does not generally suffer from a problem of water quantity. Rather, the bay has a significant water quality problem. This problem affects not only the environment, but also the region's economy. For example, the Chesapeake Bay is noted for its blue crabs. When the quality of the bay waters is under stress from human activity, the blue crab population is affected and becomes endangered. The problem of water quality in the Chesapeake Bay has been known for many years, and actions to improve the health of the bay have been proposed. Unfortunately, these efforts have not been successful. However, in May 2009, President Obama signed an executive order mandating that action be taken to restore the health of the bay and to assure that it is sustainable for future generations. The health of the Chesapeake Bay can be measured in a number of ways. One method is to measure the anoxic and hypoxic areas within the bay. These areas generally occur in the deep channels of the bay. An anoxic area contains virtually no dissolved oxygen and cannot support life. These areas are sometimes called dead zones. A hypoxic area contains very little dissolved oxygen, again, not hospitable to most aquatic species. The graphic image on the right displays the formation of anoxic and hypoxic areas in the deeper parts of the water. As we'll next show, a cause for the formation of hypoxic and anoxic areas is the inflow of nutrients, indicated by the letters N and P in the graphic, which then start a process that depletes the level of dissolved oxygen. As indicated on the previous slide's graphic and in the graphic image on the bottom of this slide, nutrients in the form of nitrogen, again indicated by the letter N, and phosphorus indicated by the letter P, as well as sediment, surface runoff, contribute to the formation of hypoxic and anoxic areas through a process known as eutrophication. As this graphic image shows, there are many sources of nutrient and sediment flow. These may come from agriculture, crop and livestock farms, urban development, and even individual homes and residences. Normal surface water flow and periodic rain and snowfall volumes gather in streams and rivers and ultimately flow into the estuary and to the ocean. Along the way, they accumulate nutrients and sediments from the landmass and transport these to the waters of the bay, where the process of eutrophication occurs. As excess nutrients enter a body of water, algae form on the surface of the water as shown in the picture on this slide. These algae form an algal bloom, that is, an increase in phytoplankton. As the algae die and decompose, they deplete the water of available oxygen, leading to the death of other organisms such as fish. Eutrophication is a natural, slow-aging process for a body of water, but human activity greatly accelerates the process. As indicated before, agriculture, crop and livestock farming contribute to the flow of excess nutrients. Crop farms apply chemical fertilizers containing N and P to fields to encourage crop growth. However, not all of these nutrients are taken up by the crops and subsequently run off or remain in the soil. Livestock farms are faced with considerable animal waste. If this is not properly gathered and treated, it too will run off into surrounding streams and rivers. Urban development results in areas of dense, impervious surfaces. Buildings, shopping malls, parking lots, streets, and roadways prevent the absorption of water into the ground, bringing again excessive runoff. As population grows, we need more homes. Some of these will be connected to municipal water supplies and proper sewage systems. However, in suburban and rural areas, residences typically use wells for water and septic systems for household waste. If not properly regulated and cleaned, septic systems can leak nutrients into the groundwater. Industrial activity may also produce excess nutrients in the form of nitrogen and phosphorus. Fortunately, industrial sites, known as point sources, are typically well regulated. So while human activity is a known and understood source of the water quality problem in the bay, nature is a significant and unpredictable source as well. In given years, the Chesapeake Bay watershed may experience excessive rain and snowfall, all of which flows through streams and rivers into the bay. And in some years, extraordinary events happen, such as depicted in the image on this slide. In September 2003, Hurricane Isabel passed over the Chesapeake Bay watershed, dropping as many as 20 inches of water in the space of 24 hours over the watershed. This single event nearly doubled the amount of excess nutrients that were carried into the bay. We cannot change the occurrence of natural events such as excessive rain and snowfall or hurricanes, but we can look for actions and policies that will affect human activity and behavior. There are numerous ideas and proposals that might help reduce the flow of excess nutrients and thereby improve and restore the health of the Chesapeake Bay. Some of these are in the form of mandated laws and regulations. Others involve monetary incentives to undertake nutrient reduction actions. And as persons become more aware of their own contribution to the problem, voluntary action and behavior change may have a significant impact. All of these proposals have merit, but we lack empirical evidence as to whether they will be effective on so large a scale. The Computing for Sustainable Water project will assess the potential impact of a large number of proposals through a detailed simulation model. The results of this project will be to discover the most cost-effective proposals to recommend for action. A term used to describe many of the proposals to be considered is a best management practice, or BMP for short. In agriculture, for example, farmers may reduce their use of chemical fertilizers or plant cover crops in the off-season. And if a farm borders a stream or river, fencing an area to prevent animals from entering the water, as shown above, will have an impact. There are even BMPs for urban and developed areas. When there is rainfall or snowmelt, municipal sanitary sewer systems are generally not designed to handle the increased load. Installing separate stormwater runoff systems is an effective way to divert this excess runoff. The image on the bottom right of this slide shows a separate stormwater storage system right here in Charlottesville, Virginia, the home of the University of Virginia. It shows a marker above a sewage grate saying "No dumping, drains to bay." It even has an icon of our famous Chesapeake Bay blue crab. So, with so many BMPs and assumptions to test, such as rates of population growth and changes in land use, the computational challenges for the simulation model are great as we systematically investigate each in isolation and then in combination. With each simulation experiment, we will calculate the total volume of nitrogen and phosphorus expected to flow into the bay, and we will also vary assumptions about population growth and changes in land use. The graphic to the right shows how we can portray these loads over time with the varying assumptions. In all, we expect to initially conduct over 1.3 million separate experiments. Each experiment will have a unique set of assumptions and combination of BMPs. Each experiment will take up to 7 hours of computing time on a World Community Grid member's computer. And as I said earlier, the computational challenge is great. In fact, we estimate that this project would require over 90 years to complete using the resources here at the University of Virginia. With the World Community Grid, we hope to complete this in less than 1 year. While the Computing for Sustainable Water project is focused on the Chesapeake Bay watershed in the United States, its results will be useful and can be transferred to many regions of the world faced with similar challenges. Our simulation model has been designed to be easily modified to other regions. We at the University of Virginia team of scientists would like to thank the World Community Grid for its generous help in hosting and running the Computing for Sustainable Water project. Most importantly, we would like to thank the countless World Community Grid members for volunteering their unused computer time to this project. And we would encourage any and all to join if you've not done so already. We look forward to sharing our discoveries with you. Thank you.
Thank you, Dr. Learmonth, for this interesting talk about the Computing for Sustainable Water project, which just started running on World Community Grid in support of Earth Day. I hope those listening will all contribute their spare processing power by joining worldcommunitygrid.org. We have time for a few questions. The first question: is global climate change factored into your research?
At the present time, we have not taken into account any of the anticipated effects or consequences of global climate change. The simulation model is designed to isolate such changes now as we monitor and try to affect what these various BMPs will do to the input of nutrients to the bay. We certainly would look forward to continued research to incorporate such ideas of climate change, so once we're finished with this project.
Do you study where the pollutants and runoff go in the ocean?
Actually, we don't. We're most concerned with the nutrient flow into the waters of the bay where they contribute to the eutrophication process that I described. Nutrients that eventually reach the Atlantic Ocean, for example, will be dissipated greatly as they reach the ocean, and it's not a problem there. But it's in the waters of the bay that we think that the most impact will be felt.
How will you be able to get the government to listen to your recommendations?
Well, as we complete this project and we received results from the World Community Grid, we will begin to analyze these results statistically, and as we formulate our observations on what's going on, we will be able to then prepare reports that we hope then to provide to the various states and to the federal government to offer them our insights as to how this process may be improved and we can improve the health of the bay.
Is the hydraulic portion of your model based on the EPA version 5 Chesapeake Bay model?
No, actually it isn't. The Chesapeake Bay Program Office has a Phase 5.3 model that has been developed over many years. We are not using the same modeling constructs as are used in the Phase 5.3 model. We've developed this one from scratch to focus on the questions that we have that we'd like to answer ourselves.
Are all the 1.3 million experiments essential? Could you describe how you came up with such a number?
Yes, the 1.3 million experiments, and I can be even more precise, it's 1,325,026 to be exact, having gone through all of the computations of how many experiments we'll take. Well, what we're going to be looking at is, in statistical terms, a fractional factorial designed experiment. We will take up to 20 different BMPs and analyze each one of them over a range of values independently, and then we will systematically start looking at the different BMPs in combination. This leads to what we would say in mathematics or statistics, a combinatorially large problem. The number of experiments to look at all of these led us to this number for our initial test suite.
What are some other watersheds in the world that need this kind of study?
Well, the Chesapeake Bay, of course, is a unique watershed. It's the largest estuary in the United States. But there are other, we estimate some 400 of these watersheds worldwide that support large populations and have similar problems with runoff and eutrophication that are affecting the quality of the water that support large urban and even suburban areas. So the model has been designed to be flexible, that once we were to complete this particular project with the Chesapeake Bay, we could then modify this code in a way that would represent additional watersheds anywhere in the world virtually.
Can you give an example of the kinds of experiments you will conduct? What kinds of measurements you will take, where you will take them, how you will take them?
Yeah, so as I mentioned, with these different best management practices, our base model consists of about 34,000 what we call land areas in the Chesapeake Bay watershed. And traversing those land areas, we have about 1,069 rivers, streams, and creeks and bodies of water that ultimately flow into the bay. With a base model, with a population in the year 2000, we've estimated there would be about 4 million households, each of which is represented in the model. And then we would vary, for example, the percentage of those households that are connected to a municipal or public sanitary sewer system versus the number that are connected or use, for example, septic systems. And as we vary the percentage of the households that are connected to proper sewage systems versus those that are on septic systems, we'll be able to experience the change in the rate of flow of nitrogen, phosphorus, and sediment into the bay. We would then take another best management practice, perhaps agriculture moving towards the planting of cover crops in the off-season, which then has the possibility of holding the soil during the off-season, the winter, here in North America, and seeing what the effects of large-scale agricultural deployment of cover crop policies, how those would affect the nitrogen, phosphorus, and sediment loads. So systematically, we'll go through these different possible solutions to measure the effect in terms of the total load of nitrogen and phosphorus and sediment that reached the Chesapeake Bay under the experimental conditions.
Do you know of other competing groups working on the same problem?
Frankly, we don't know. We think that the work that we're doing here is unique. A model of this size and caliber, I think, given the computational challenges to do something like this, our opportunity to work with the World Community Grid has positioned us very, very luckily, shall I say, that we have the opportunity to do these experiments with the World Community Grid. It is a computational challenge, but it's one that is very worthwhile as we look at the water challenges that the globe is facing.
How does this compare to the Computing for Clean Water project on World Community Grid?
We think that the Computing for Clean Water project at Tsinghua University in China is complementary to this. Our colleagues at Tsinghua are looking at nanotube filtration as a method to take water that, such as the water in the Chesapeake Bay, that's of subpar quality, and filter that water to return it to a state that can be usable by the population that it's supported. So while we're looking at the water quality problem as a flow problem and how the problem is caused, our colleagues at Tsinghua are on the other side of the equation, if you will, looking at methods to take water that's of subpar quality and clean it up for reuse by human beings.
Is the ultimate objective of the research to prevent further degradation of the bay, or is the goal to reverse some of the degradation? That is, can the degradation be reversed or just slowed?
Well, if we can come up with an effective set of policies, as measured by this simulation model, that we can use to inform state and local regulators and federal regulators, if we can reduce the inflow of nitrogen, phosphorus, and sediment into the bay from non-point sources, non-point being agriculture, land development, and even us as individual citizens living in here. What we would hope to do is to significantly reduce the inflow of these nutrients and then look to the US EPA and see how this affects the size of the anoxic and hypoxic areas in the bay. This is something that the US EPA does annually, and we would hope that by our recommendations we would see both the restoration of the bay's health to an acceptable quality and effective policies that will enable us to maintain the health of the bay for future generations.
One of the listeners would like to congratulate you for being such a visionary. What motivated you to take on such a problem? And is there anything else we can do to help?
Well, this project grew out of another project we have here at the University of Virginia called the UVA Bay Game. This is a participatory simulation with a much more highly aggregated and, dare I say, simplistic model of the Chesapeake Bay. The Bay Game allows individual players, students, members of the community, regulators, to play roles as farmers and land developers and watermen and regulators and learn how the interaction of these different communities lead to solutions to bay problems. Our faculty group here at the University of Virginia, which spans now 8 of the 11 schools at the university, decided that what we really ought to have is a much more detailed simulation model to really drill down and see how these actions with respect to human behavior and the natural occurrences in the bay could be measured in a more fine detail than to inform our policymakers. So this particular project grew out of that, the UVA Bay Game, and we were just delighted that IBM's World Community Grid was available to us to address the computational challenges that we see with this project.
Thanks again, Dr. Learmonth, and those attending. Sorry if we didn't get to your question. Please use our forums at World Community Grid to post any additional questions. This concludes our webcast.